Principal strains are strains in the direction of the principal stresses. Let this material be isotropic and it's subjected to three-dimensional principal stresses sigma 1, sigma 2 and sigma 3, which are mutually perpendicular to each other. Then the principal strains epsilon 1 or E1 can be written as per Hooke's generalized law, and taking lateral strains into consideration can be written as E1 is equal to sigma 1 by E minus mu sigma 2 plus sigma 3 by E. Sigma 1 by E is the longitudinal strain, whereas mu sigma 2 plus sigma 3 by E is the lateral strains corresponding to stresses sigma 2 and sigma 3, which are at perpendicular direction to sigma 1. So simplifying, we can write E1 is equal to 1 by E sigma 1 minus mu sigma 2 plus sigma 3. Similarly, E2 can be written as 1 by E sigma 2 minus mu sigma 1 plus sigma 3. Mu is the Poisson's ratio and E3 is similarly 1 by E sigma 3 minus mu sigma 1 plus sigma 2. Generally, we consider two-dimensional system, so E3 is equal to 0 in two-dimensional system, and we can write E1 minus E2 is equal to 1 by E sigma 1 minus mu sigma 2 plus sigma 3 minus sigma 2 plus mu sigma 1 plus sigma 3, which we can write equal to 1 by E sigma 1 minus sigma 2 1 plus mu. Let us write it in another form: sigma 1 minus sigma 2 by 2 into 2 1 plus mu by E. From the theory of principal stresses, we know that sigma 1 minus sigma 2 by 2 is tau max, or the maximum shear stress, and we also know that E by 2 1 plus mu is equal to Z, where G is the shear modulus or modulus of rigidity. So we can write tau max by Z, which is nothing but maximum shear strain, or we can write psi max. So in two-dimensional system, we can say the maximum shear strain psi max is equal to difference of the principal strains E1 minus E2. In three-dimensional system, let us assume E1 is maximum and E2 is minimum of the three, E1, E2 and E3, the corresponding strains. In that case, psi max will be equal to E1 minus E2, or we can say greatest difference of principal strains. Understand concept of plane strain. Strain caused by normal or direct stresses are called normal strain, and strain caused by shear stress is called shear strain. Let us take a plane element of a strand material, say plane in XY plane. It is subjected to three strains: normal strain in X direction, EX, normal strain in Y direction, which is EY, and shear strain relative to OC and OA, psi. All other strains, say EZ, psi YZ, and psi XZ, are non-existent. So if a plane is under strains in X direction EX, in Y direction EY, and relative to OC and OA a shear strain psi XY, then the system is plane strains. So we can summarize plane strain as: on a plane element OABC of a material under strain situation is subjected to three strains. First, the normal strain along X direction EX, normal strain along Y direction EY, and shear strain psi XY. Then it is called plane strain system, like plane stress system. So in plane strain system, Ez is 0, psi xz is 0, and psi yz is also 0. In diagram 1, Ex is the departure from this point to this point, and in figure 2, Ey is departure of this point to this point, whereas psi xy is this angle. Ex, Ey, and psi xy are frequently called E1, E2, and simply psi. Right. Like plane stress system, we had transformation equations to find out stress at a plane inclined at theta degree. We have transformation equations for plane strain also to find out strain in direction inclined at theta degrees from the direction of Ex, or the strain along the x-axis. So after the strain, point P is projected to B dash. So this is the final position of the B after the strain Ex in x direction, Ey in y direction, and psi, the shear strain, with respect to OC and OA. Now we have transformation equation to find E theta, that is strain along the theta direction from the direction of x-axis, and we also have psi theta to find the shear strain at an angle theta. So if a point D is strained to D dash, then psi theta will be denoted here. This point is C dash, the strained position of C, and this is perpendicular on the diagonal OB dash. So the angle between these two lines is the psi theta, or the shear strain at angle theta. So it can be proved that E theta is equal to 1 by 2 E1 plus E2 plus 1 by 2 E1 minus E2 cos 2 theta plus 1 by 2 sin 2 theta psi. Similarly, for psi theta, we have expression 1 by 2 psi theta is equal to minus 1 by 2 E1 minus E2 sin 2 theta plus 1 by 2 psi cos 2 theta. In these equations, E1 is Ex, or the strain along x direction, and E2 is Ey, or the strain along y direction. From the transformation equation for normal strain, E theta is equal to 1 by 2 E1 plus E2 plus 1 by 2 E1 minus E2 cos 2 theta plus 1 by 2 psi sin 2 theta. It is evident that the normal shear strain vary with theta. So the maximum and minimum normal strains are called principal strains, as it was called principal stress in the case of stresses. And by differentiating these equations with respect to theta and putting the value to 0, we can find out epsilon 1 and epsilon 2, which are the maximum and minimum normal strains or major and minor principal strains, such that epsilon 1 and epsilon 2 are equal to E1 plus E2 by 2 plus minus root of E1 minus E2 by 2 whole square plus psi by 2 whole square. And direction of the principal strains are such that tan 2 theta ps is equal to psi upon E1 minus E2. It can be proved that direction of principal strains are the very direction of principal stresses. The angle of principal stresses is such that tan 2 theta p is equal to 2 tau by sigma 1 minus sigma 2. Putting value of psi is equal to tau upon z, and E1 is equal to sigma 1 upon E minus mu sigma 2 upon E, and E2 is equal to sigma 2 upon E minus mu sigma 1 upon E. We can prove that psi upon E1 minus E2 is equal to 2 tau upon sigma 1 minus sigma 2, where E1, E2 are the strains along xy direction and sigma 1, sigma 2 are the stress along x and y directions. Psi is shear strain and tau is shear stress. So the direction of principal strains are the same as the direction of principal stresses. The maximum shear strain psi max is given by relation 1 by 2 psi max is equal to root E1 minus E2 by 2 whole square plus psi by 2 whole square. The minimum shear strain would be of same magnitude but in negative direction, so we can say maximum and minimum shear strains are plus minus root E1 minus E2 by 2 whole square plus psi by 2 whole square. And direction of maximum and minimum shear strains 2 theta SS is such that it is equal to 2 theta PS, that is the direction of the principal strains, plus minus 90 degrees, or we can say theta SS is equal to theta PS plus minus 45 degrees. Now let us see Mohr's circle construction for plane strain. If E1 and E2 are the strains, normal strains in x and y directions, and psi is the shear strain, then to construct Mohr circle from the origin we will draw a line of length E1 such that from origin O and A the length is E1. Then from point O we will draw another line equal to the magnitude of E2. So point B is such that OB is E2. At point A, for positive strain, we will draw 1 by 2 psi downward, and from point B we will draw 1 by 2 psi upward. Join these two lines F and G. It would pass from the midpoint of A and B, say it is C. Then draw a circle with C as center and CF or CG as radius. So let us draw a circle with C as radius and CG or CF as radius, C as center. So this is the Mohr circle, and as we have obtained principal stresses by the intersection point of x-axis and the circle, the point O G will be the principal strain, epsilon 1 will be equal to OG, and minimum principal strain epsilon 2 would be OH. OH is the minimum distance from the origin of the circle, and OG is the maximum distance of any point on the circle from the origin. Similarly, maximum and minimum shear strains will be obtained by intersection of y-axis. So D dash and D are the intersections of y-axis and circle. CD dash will be maximum shear strain and CD will be minimum shear strain, which is of equal magnitude but in negative direction. So this completes the brief of the theory of plane strain, and we will go to problems after this video.